Okay, we are off to chapter 3 here. So once again, this material here is going to be exam 2 material. And as we talked about last time, really the only thing from chapter 3 that you need to know for the exam on Monday is what electronegativity is and its general trend, like we talked about the other trends. We'll always talk more about electronegativity in this chapter. But again, for chapter exam 1, that's all you need to know from it. All right, so in this chapter, chapter 3, followed by chapter 4 afterwards, we're going to really talk about bonding and different aspects of bonding. We'll talk about different types of bonding. We're going to talk about drawing Lewis structures. Chapter 4, we'll get into geometry, polarity, and all that kind of stuff. And then afterwards, we will come back to chapter 3. So we're going to do everything, I think, in chapter 3, except for maybe the last section, which is about naming. So we'll come back to naming after we do the rest of the bonding and stuff like that. All right, so let's talk about bonding. We use Lewis dot symbols to represent bonding. And Lewis dot symbols are also sometimes referred to just as electron dot symbols. And when atoms basically interact to form a chemical bond, it's really only the outer region that sort of comes in contact with each other. And as we talked about with electron configuration in the last chapter, that is going to be our valence electrons, which are really the ones that are involved in bonding. So remember that, we sort of have two types of electrons. They're sometimes classified within an atom. So if we looked at something, say like carbon, which is 6 up there, 1s2, 2s2, 2p2 in this case. Remember that these guys here are on the highest energy level, so 2 and 2 is 4 valence electrons. The ones that are lower in energy, closer to the nucleus, as we talked about, again, are referred to as core electrons. And bonding is all about the valence electrons. They are, again, those outermost electrons, the furthest away from the nucleus. So it does sort of make sense as two atoms come together. They are the first ones that basically sort of come in contact with each other. Based on those periodic trends that we talked about yesterday, they're also the ones that, frankly, are not held as tightly as all the other electrons. And that allows them to either, in certain situations, be sort of lost, and in other situations, allows them to sort of share with one another. Remember that the valence electrons equals the group number. So obviously everybody on group 1 in the periodic table has 1 valence electron, 2, 2, 3, 4, 5, 6, 7, and then obviously 8 there with our noble gases. So you can definitely write the electron configuration to figure out the valence electrons, but much easier just to look at the periodic table and grab that group number, and you'll be able to determine what it is. So we show the valence electrons, which again are the ones that are involved in bonding, by using Lewis dot symbols. Lewis dot symbols are pretty much the symbol and 1 dot to represent each of the valence electrons that are there. So we use the symbol, and there's really kind of no rule other than usually no more than 2 per side. So you could basically do kind of 2 dots per side as the maximum, which obviously if we did fill up all the sides there, that would give you 8 valence electrons, which would be equal to our noble gases. So a thing that we will see in bonding that we talked a little bit about, I think, yesterday as well, that frankly is the goal of all types of bonding, is for everybody to basically achieve the same electron configuration as the noble gases. Again, noble gases being very, very stable. They're chemically inert, and that's pretty much what everybody wants to achieve, and they do it through bonding. And in certain cases, as we'll talk about, it's done through transferring electrons. You're losing and gaining, and in other cases, it's done through sort of sharing electrons, but the ultimate goal is to basically achieve that kind of normal gas configuration. Here's some Lewis dot symbols, and again, you can see everybody there in group 1 has 1, 2, and again, we're using our representative numbering here, so 3, 4, 5, 6, 7, and 8. Couple or one exception would be helium, even though it is part of group 8. It only frankly has 2 electrons total, so it cannot have 8 electrons. So helium is 1s2, so it uses its total 2. But everybody else there in group 8 will have 8 valence electrons, obviously, except for helium. Now, there's really 2 types of bonding we're going to kind of talk about in this chapter, and the first type is ionic compounds. And in ionic compounds, it is always really between a metal and a nonmetal. And really based on those sort of periodic trends that we talked about yesterday, what typically happens is with most metals, they have, again, very low ionization energy. They have low electron affinity. They have low electronegativity. All that means is pretty much our metal will pretty much always be the one that's going to transfer electrons over to our nonmetal. And with the periodic trends of our nonmetals, which have very high electron affinity, very high ionization energy, and very high electronegativity, those are all things that want them to keep their electrons and also kind of gain other people's electrons as well. So when these 2 guys come together, we definitely get a transfer of electrons from the metal to the nonmetal. The result of that is we will form our cation, which is positively charged, and our anion, which is negatively charged. And it's important to, again, remember that in an ionic compound, we have absolutely no sharing of electrons there. It is strictly the electrostatic attraction, the attraction between the positively charged ion and the negatively charged ion that is holding that unit together. So absolutely, again, no sharing of electrons here. And we have those complete transfer of electrons from one to the next. And that is different as we'll get into covalent bonding. And covalent bonding, that is typically between 2 nonmetals. And when we get really 2 nonmetals together based on our periodic trends there, they are both pretty much going to want to hang on to their electrons. They're both going to want to kind of gain electrons as well. So because they're located in a similar spot on the periodic table, they have similar properties. So what ends up happening in this case, as I mentioned yesterday, we really don't get the transfer of electrons. So what they both sort of agree upon is, well, I'm not going to give up my electrons. The other one's like, I'm not giving up my electrons. So they're going to end up just sort of sharing the electrons. So when we get a covalent bond or a covalent compound, that's with 2 nonmetals that end up with the sharing of electrons. Now, the sharing of electrons, as we'll talk about, it may be equal. So, sometimes they participate in sharing those electrons sort of equally between the 2 atoms, or it may be unequal. And the result of either the electrons being shared equally or unequally does result in 2 different types of covalent bonds. As we'll talk about, one is referred to as a polar bond, and one is referred to as a nonpolar bond. So the general rules are atoms with very low ionization energies tend to form cations. Remember, again, ionization energy is the energy required to remove an electron. So if you have very low ionization energy, it doesn't take a lot of effort to remove the electron. And those with high negative electron affinity tend to form anions. Electron affinity, again, is that energy change that occurs when somebody gains an electron. So a high electron affinity means that they're more apt to sort of gain electrons and become negatively charged. Any questions on that there? So general rule basically tells us that, our metals, really a lot of guys in group 1 and group 2 will definitely form cations. And our guys kind of in our non-metal region there above the staircase, like our halogens, oxygen, and so forth, will form our anions. So let's talk about the formation of this. If we look at lithium fluoride, for example, And if we write the electron configuration for lithium, it is 1s2, 2s1. And if we do the electron configuration for fluorine, it is 1s2, 2s2, 2p5. Again, this would be the valence electron here for lithium. And we could also look on the periodic table, see lithium is group 1, so obviously it has one valence electron. For our fluorine here, it is group 7 on the periodic table, and those are the 7 valence electrons that we have for fluorine. Now, if we were to show this type of bonding, first off, we know right off the bat that this hopefully is a metal. This is a non-metal. And pretty much when you see that combination, that should scream to you that we are dealing with an ionic bond here. And that also should tell you that we're not going to have any type of sharing of electrons. We are going to have the transfer of electrons from the metal to the non-metal. And we can represent that with Lewis dot symbols by taking our lithium and drawing our Lewis dot symbol. We can write our electron configuration underneath it. 1s2, 2s1. Is going to go and add to our fluorine, which again is group 7. So it will have 7 valence electrons here. And I'll pop down there, 1s2, 2s2, 2p5. So because this again is a metal, non-metal situation, what's going to happen is our lithium is going to decide, because of its periodic trends, I don't want to hang on to that electron. It will transfer it over to the fluorine there. The fluorine will definitely accept it because it has all those properties of I would like electrons, so no problem, bring them on over. The result of that is we will then get a lithium that at this point will now become positively charged because it lost an electron as it transferred it over to fluorine. And we will also get a fluorine that picked up an electron and then would become negatively charged as well. And now what we just formed here is an ionic bond. There is absolutely no sharing of electrons here. That is why when you draw sort of Lewis structures for ionic compounds, you do include the charges. And that indicates that there is no electrons being shared. A lot of times, like I did here, people will put a bracket at least around one of them. Sometimes they'll put it around both of them, but usually do some type of bracketing around those guys. So no sharing of electrons. We have a complete transfer of electrons in this particular case. And if we look at what happens to our electron configuration for each of these guys, it is the lithium that pretty much laid up and got rid of this electron in there. That means when lithium has a +1 charge, it ends up as 1s2. And who is number 2 on the periodic table? It is helium, right? That one electron that it gave up will end up over here in this p subshell as it has room for it. And that moves our configuration for fluorine with a -1 charge, or fluoride, to 1s2, 2s2, 2p6. That is 2, 4, and 10 electrons. And on the periodic table, number 10 is neon. So as we see here in the case of the formation here of this ionic bond, both elements are able to achieve the same electron configuration as a noble gas. Lithium, by losing an electron, is able to go backwards and basically achieve helium's configuration. And fluorine, by gaining the electrons, is able to go forward on the periodic table and basically achieve neon's configuration. And again, as I mentioned before, that is pretty much the goal of bonding, is to get everybody into the same electron configuration as those noble gases. Any questions on that there? And once again, no sharing of electrons, just that positive negative attraction. So once again, that is held together by what's sometimes referred to as electrostatic attraction, positive, negative attraction, opposites attracting to each other. And, you know, sometimes people having trouble figuring out, is it an ionic bond or not? And that's pretty much all you need to look at to figure out is it an ionic bond is to see you have a metal and a non-metal basically come together. You don't have to think twice about it. It's always going to be an ionic bond. Never going to be any sharing of electrons that occur there. Any questions on that? Okay. So let's take a look at another example. Let's look at calcium and oxygen for calcium oxide. So calcium, if we look at the periodic table, there is 20, and it would have 2 valence electrons as it is group number 2. And if we did a little electron configuration, that is argon 4s2. These would obviously be the 2 valence electrons that we have going on there for calcium. We add that to oxygen, which is group number 6 on the periodic table, means that it does have 6 valence electrons here. And if we did the configuration for that, 1s2, 2s2, 2p, 2, 4, that's all right. That is group 6 over there. 4, there you go. And that would be is 6 valence electrons here. The guys right there. So in this particular case, calcium is going to give up some electrons since it is our metal. And once again, we know this is a metal. This is a non-metal, which is oxygen. Once again, telling us this is a ionic bond that is happening here. So in this case, it's always the metal that gives up the electrons. So calcium is going to send over an electron over here. Now, if calcium just loses 1 electron, is that going to get it to where it needs to be? If we look at the periodic table and it loses 1 electron, it's just going to back up to potassium, which is not a noble gas. So here, calcium is going to want to lose both of those electrons so that it can back up 2 spaces there on the periodic table. The result of that is here calcium will once again become positively charged and it will become a +2 charge as it lost 2 electrons. Once again, it's going to be these 2 electrons that it loses, which means it's going to back up to argon's configuration, which obviously is a noble gas. And again, the purpose here, our oxygen there is going to accept the 2 electrons. And when oxygen accepts those 2 electrons, it will now become negatively 2 charged. Once again, we have now just formed an ionic bond here between these 2 things. No sharing of electrons, positive, negative attraction to each other. Those 2 electrons are going to fill in over here in our p subshell. And that is going to get us to 1s2, 2s2, 2p6, which once again is 10 electrons and is the same electron configuration there as neon. So once again here we see by calcium losing 2 electrons, it allows both calcium to achieve noble gas configuration and also our oxygen to get to that noble gas configuration, which ultimately is what the goal of this process is. Any questions on that one there? So what happens if we sort of take a couple of these things and put them together? So let's say we took our calcium and we put it together with our fluorine that we saw, say, in the first example. Let's see what happens in that case there. So let's say we took calcium, which has its 2 valence electrons that we just saw there, our argon 4s2. And we put it together with our fluorine, which was group 7 there on the periodic table. 1s2, 2s2, 2p5. So when these 2 guys come together, once again, we have calcium, which is a metal. We have fluorine, which is a non-metal. So we should expect a transfer of electrons. So what's going to happen here is this calcium here is going to lay up its electron over here. At this point, can that fluorine take any more electrons? When it gains that 1 electron, it now has 8, which makes it happy. Problem, though, is calcium is still stuck with 1 electron that it needs to get rid of, right? So in this particular case, this would not be beneficial to calcium, as it again would only get it back to potassium. It needs to really lose 1 more electron, but that 1 fluorine cannot do it. So in this case, we actually need not 1 fluorine, but we actually would need 2 fluorines here. And it is that second fluorine that then could achieve that second electron from the calcium. The result of that is, at this point, the calcium now can dump both of its electrons and become +2. And again, it's going to be these 2 electrons that get removed. That brings that calcium to argon's configuration. Now, each of the fluorines in this case will actually only pick up 1 electron each. And that would give us a fluorine that has picked up 1 electron and becomes negatively charged. And that will give us a second fluorine that also picks up 1 electron and becomes negatively charged. Once again, here, there's no sharing of electrons. It's the attractive force between the positive and negative that kind of holds each other together. And in reality, probably didn't have room. This second negative would be maybe drawn on that side to keep the negatives apart from each other. But in terms of fluorine, each of the fluorines will pick up 1 electron into his p subshell. So 1 electron would go into his p subshell of each, and that will give each of these guys the same configuration as neon. So all 3 of these guys in this particular case achieve noble gas configuration. Each of the fluorines get to neon by picking up 1 electron. Calcium goes backwards to argon by losing 2 electrons, and again makes everybody really happy in that particular case. That is why, as you might remember from maybe nomenclature from the previous class or whenever you deal with it, when we take an ionic compound and we have something that has a positive charge like calcium and something that has a negative charge like fluorine, we always want to put it together so that the overall charge equals 0. And in this case, this is why we would need 2 of the fluorines. +2 and -2 give us a 0 overall charge and gives us the proper formula for calcium fluoride, which would look like this. And really the reason why we put those guys together in a way that gives us the overall charge of 0, and the simplest way to do so is that will allow everybody there to achieve noble gas configuration. So that's really the purpose when we do ionic compounds and nomenclature and putting formulas together. Always positive, negative guys come together in the simplest way to get the overall charge to 0. And then again, the purpose of that is that allows everybody to basically achieve noble gas configuration. Any questions on any of that there? All right, so this obviously represents ionic bonding. This is the type of bonding that we definitely will always see when we put a metal and non-metal together. And once again, if you do draw these things, which you do need to be able to draw these things like we've just been doing here, you do need to make sure you include the charges when you are done there on the right-hand side. Any questions on any of that there? All right, then let's talk about the other type of bonding, which is covalent bonding. And our good guy named Lewis suggested bond formation here. And clearly in PowerPoint, things missed a whole bunch of spots there. So we'll fix that up there. So this would be that. I think it's okay on your handout, I think, maybe there. And that looks like that. So covalent bonding is really the other sort of main type of bonding that we talk about. And once again, kind of like what we have with ionic bonding, that when we recognize that as a metal and non-metal is going to be ionic, when you see pretty much just all non-metals involved is going to be covalent bonding. So this is basically 2 non-metals together. And once again, here we're going to have sharing of electrons in the case of covalent bonding. So Lewis suggested the role of electrons in chemical bonding, and we could represent a bond. So for example, if we had our 2 hydrogens, one hydrogen plus another hydrogen. In this particular case, they're both hydrogen, which means pretty much they have the identical set of periodic trends, same ionization energy, electron affinity, electronegativity. So because they're pretty much the same and they're pretty much both nonmetals, they both want to hang on to their electrons. So what's going to happen is instead of transfer of electrons like we see in an ionic compound, we are going to get a sharing of electrons that occur. The result of that is we will get a bond that occurs between the two hydrogens, where the electrons that are between them, which are represented in this case by dots, does count for each hydrogen. So the hydrogen on the left would count the two electrons there for itself. The hydrogen on the right would also account for the two electrons there. And that means that in this case, unlike an ionic compound or an ionic bond, we are achieving basically 2 electrons for each of these hydrogens by actually sharing of electrons. So here by sharing of electrons, they each achieve 2 electrons. That is actually okay for hydrogen because if we look on the periodic table, we have hydrogen right there, and to the right of hydrogen is helium. So one very important rule of bonding is, frankly, hydrogen only needs 2 electrons. So hydrogen only needs 2. Hydrogen should never have more than 2 electrons. So if you find yourself drawing things and you're putting multiple bonds to hydrogen, or you're putting dots all the way around hydrogen, it is definitely wrong. You should put an X on it yourself. Save me the trouble. Yes, it is wrong for sure. People like to do that for some reason, like triple bonding hydrogen and dots all over the place. So hydrogen only, because of its location, just needs to get to helium, which is 2, and that is good enough for it. Pretty much, though, everybody else will need the magic number there of 8, which is kind of the number that everybody achieves. Any questions on that there? You could represent this with Lewis dot symbols or Lewis structure here by using dots, or we oftentimes, for these type of electrons, which are referred to as bonding electrons, we can use a line to represent it as well. I personally use lines to represent sort of electrons in a bond, but you can use dots. So obviously one line represents 2 dots, and that are a pair of electrons, and that's what is referred to as a single bond. If you have 2 lines, that would be representing 4 total electrons or 2 pairs of electrons. That would be a double bond. And obviously 3 lines would represent a triple bond, which would also represent 6 total electrons, or 3 pairs of electrons would be a triple bond. So in covalent bonding, a lot of times we will use a line to represent those electrons within the bond. Or if you want, you could still obviously use dots as well. Any questions on that there? So in a covalent bond, the electrons are shared, that is being shared between the 2 atoms, are both attracted to the nucleus basically in both atoms. So if you think about it, you know, you got like an element on this side, you got an element on this side, and we have electrons that are being shared. You think about in the middle, obviously there's like a positively charged nucleus. So these electrons are sort of attracted to this guy, but yet they are also attracted, obviously, to the nucleus of the other guy. And that sort of mutual attraction is sort of what locks those electrons into place between the 2 atoms. As we'll talk about later in this chapter, sometimes, you know, the electrons are attracted perhaps a little bit more to one guy versus the other, and that creates a different type of covalent bond, but they're still being shared. So the idea of covalent bond, whether it is, as we'll talk about, nonpolar covalent bond or polar covalent bond, the idea is there's some aspect of sharing happening, either equal sharing or unequal sharing, and that is completely different than what we see with ionic bonds, where there is absolutely no sharing of electrons. A complete transfer has occurred. So if we look at F2 in this case, fluorine is 1s2, 2s2, 2p5. In this case, once again, they're both fluorine, so they're just going to decide we're going to share those electrons The result of that is you could get your fluorine that looks like there with all the dots, or you can use the line in between to do so. When we look at this fluorine, which is F2, and we look at what is happening for each of the fluorines in this particular case, again, those electrons in the middle will count for the fluorine on the left, which means if we count it over there, he has 8 electrons, again, through sharing those guys in the middle. And same thing here for our guy on the right. Those two will count for him as well, which will give him 8 electrons. 8, again, is a really sort of important number, obviously, in covalent bonding. 8 is what is referred to as the Octet Rule, and that is pretty much what everybody is shooting for, except for hydrogen. Everybody is shooting for 8 valence electrons. And that, once again, is because if we go to the periodic table, number 8 up there is the noble gases. So again, in this case, by sharing of those electrons, going to allow everybody to achieve that noble gas configuration, which is sort of the same result as what we see with our ionic compound through transferring of electrons. Any questions on that there? Now, when we do look at something like fluorine here, there are 2 different types of electrons that we come across. All these electrons that are dots that are not involved in any type of bonding. And we know they're not involved in bonding because there's frankly no element on the other side of them, so they're just kind of there. Those are what are referred to as non-bonding electrons, which is what most books call it these days. I personally call it lone pairs because that's kind of what they beat in my head when I went to school. But so if I say lone pairs, it's the same thing as non-bonding electron. It is all the dots that are there in your Lewis structure. The other type of electrons that we were just talking about is the ones that actually are involved in bonding, and that would be obviously these guys right here. And they also have a very creative name. They are known as bonding electrons. So bonding electrons are obviously the electrons that are involved within a bond between 2 elements. Non-bonding electrons are basically lone pairs of electrons. They are not involved in bonding, but they're still there. They do affect certain things, as we'll talk about in this chapter, maybe next chapter as well. You should always, when you draw Lewis structures, as we'll talk about a little bit later on, should always make sure you include, obviously, both of those things. You should always include the bonding electrons, and the non-bonding electrons should also always be shown. So a Lewis structure, again, is a representation of covalent bonding, again, using the dot symbols to help us show it with either lines or dots for bonding electrons and definitely dots for non-bonding electron. It's important to remember that although when we look at a Lewis structure, really the only electrons that we are actually seeing are the valence electrons. Each of those elements have other electrons, the core electrons, but since they're not involved in bonding, they're not shown typically in the Lewis structure, but they're still there. But really, in terms of bonding, it's just those valence electrons that are important. So if we drew the Lewis structure here for water, we see the same sort of thing as we've been talking about. Here in this case, it is the oxygen. It is the oxygen by sharing actually with both hydrogens here, able to achieve 8 electrons. And by that oxygen sharing with both of those hydrogens, that allows each of the hydrogens to achieve 2 electrons, which again makes it happy and obviously makes the oxygen happy. That is, again, the goal of covalent bonding, and things will continue to make bonds until they get to that 8 electrons. So that is really why in certain cases, certain things are double bonded or triple bonded. That is a way that allows everybody to achieve that octet rule, as we'll talk about. And sometimes things can achieve it, as we see here, with just single bonds, they can achieve it. But sometimes you do need multiple bonds, double bonds, or triple bonds to sort of achieve that octet rule. And again, that's sort of the basis is why things sometimes have double bonds or triple bonds. So obviously 8, as I've been talking about, is an important one, and 8 is what is known as the Octet Rule, and that pretty much means that everybody but hydrogen will once again continue to make those bonds until they do achieve those 8 electrons, putting them in the same category really as noble gases. And again, by sharing of those electrons, they're able to complete their octet. Hydrogen, once again, only to keep that in mind. That also means that pretty much hydrogen should always be on the outside and pretty much just one line drawn to it. If you're using the line to represent bonding electrons, if you're using dots to represent bonding electrons, it should look like that. You should never have hydrogen in the interior, because if it does, it's definitely going to have way more than 2 electrons to it. So hydrogen always got to be on the outside, basically with just one line drawn to it. And again, no dots around it when you do that. That is sometimes referred to as the Duet Rule there for hydrogen. That again just needs 2 electrons. So we talked about it just a second ago here, but once again, a single bond is one pair of electrons that's being shared between 2 atoms. So basically 1 line, 2 dots, 1 pair of electrons, which is a total of 2. Again, as I mentioned before, sometimes things do need double bonds to reach the octet rule, and that is what we see here with CO2. The oxygen needs to form actually a double bond on both sides of the carbon there to allow each of the oxygens to get to 8 electrons. Really, is to allow carbon in the middle actually to get to 8 electrons is really why it's doing that. And again, by doing so, the carbon in the middle, by making a double bond on the right and left, ends up with 8 electrons. And each of the oxygens, by making the same double bonds, also end up with 8 electrons. So once again, sometimes double bond is needed to do that. 4 electrons are 2 pairs of electrons there are represented by it. Ethylene is this guy here, and in this particular case, the carbon, by making the double bond there with its other carbon, ends up getting 8 electrons. Again, each line represents 2 electrons, so 2, 4, 6, 8. And the carbon on the right-hand side, which pretty much is the same bond, so an organic guy here, ends up with 2, 4, 6, 8 electrons as well, again, each line. So by sharing really the 4 electrons in the center there, it's able to achieve it. And again, each of the hydrogens here, by sharing electrons, have 2 electrons, which again makes each of the hydrogens happy in this particular case. Any questions on that there? As I mentioned before as well, sometimes, you need to go to a triple bond as well to get to that octet rule. And in a triple bond, we have this sharing of, again, 6 total electrons, are 3 pairs of electrons. And that's what we see here with nitrogen. By making that triple bond in the middle, it shares those 6 electrons with its 2 non-bonding electron pairs, gives it our 2 non-bonding electrons, gives it 8 total electrons and 8 on the other side. And that is acetylene, which has a triple bond in the middle. Again, this carbon, by sharing those triple bond, gets to 8, and the same thing for the guy there on the left. And once again, our hydrogens in this case both achieve 2 electrons. I will put a side note, and we'll talk about when we talk about officially sort of drawing Lewis structures and covalent bonding. Sometimes people like to double bond and triple bond like right out of the box. Just like I'm going to keep drawing lines. It looks great. It looks more science-y and more chemistry-like. But you really should, in a lot of cases, kind of start with single bonds and then use double bonds or triple bonds to maybe fix a problem where somebody does not achieve the octet rule. Again, a lot of times just double bonding and triple bonding out of the box is not usually going to give you maybe the best structure. Sometimes it will, but sometimes it will not. So let's talk about, in this type of bonding where we're sharing electrons, what really helps us determine between 2 individual elements, will they share those electrons equally? Will they share it unequally? And it really is electronegativity, which is the overwhelming thing that we look at to determine whether or not just the electrons between these 2 atoms, will they be shared equally or unequally? As we talked about in the last chapter, and we'll see here again, electronegativity is the ability of an atom to bring electrons towards itself. And as we talked about, as we'll see here in just a second again, a reminder, as you go up and to the right on the periodic table, electronegativity increases. As you go left and down on the periodic table, it decreases. And it is our guy right there. Fluorine is the most electronegative element that you could have, and its location is pretty much up and to the right. The only thing further than fluorine is the noble gases, but since the noble gases are already stable, they're unreactive. That's why we kind of stop there at fluorine, because the noble gases are perfectly fine the way they are. We also saw through the lab that we did the other day, right? Reactivity increases at group 7 as you go up, right, towards fluorine. So that all makes sense, you know, based on what we saw. So electronegativity enables us to distinguish, you know, what happens when we have really covalent bonding, and what happens when two atoms come together and how they're going to share the electrons. So if we had something like the hydrogen that we saw before, where we have basically this, in this case, those electrons in the middle are going to be shared by each hydrogen pretty much equally. They're going to spend about the same amount of time. That is because you can think of it like a magnet, if you will, right? Hydrogen's on this side, it's basically identical to this side. So the kind of pull on those electrons are going to be equal, you know, going in both directions. So we'll get sort of an equal pull on those electrons, an equal distribution. My little fan in here is the electron density. We'll have sort of an equal sharing of those electrons on both sides. Whenever we sort of get an equal sharing of electrons on both sides, it is what is referred to as a nonpolar covalent bond. Or most people drop the covalent part and just call it a nonpolar bond. So in a nonpolar bond, or a nonpolar covalent bond, which is essentially the same thing, we get basically equal sharing of electrons between the two atoms within that bond. Same thing happens when we deal with fluorine, right? We got the two fluorines. Once again, they're both fluorine, and we would expect kind of this fluorine to pull the electrons sort of equally on both sides. And this also would be a nonpolar bond. So 100% of the time, if you got only two things, or you're looking at a bond and both of the things are the same element, it should always be nonpolar, because it's basically like the same sort of force pulling on those electrons. The result of it sort of sharing the electrons equally is it sort of creates like a neutral bond. That means there's sort of equal distribution of those electrons. There's no side of the bond that's more positive. There's no side of the bond that's more negative. It's sort of nice, perfectly equally shared between them. Now, what happens, though, if we take something like hydrogen and fluorine and put it together? We no longer have now the exact same two things sharing the electrons. And in fact, if we look at the periodic table, we see hydrogen kind of on the left there, we see fluorine on the right, and we already know that fluorine is actually more electronegative than hydrogen. That means if fluorine is more electronegative than hydrogen, would the electrons be more attracted to fluorine or less attracted to fluorine? It should be more attracted to fluorine, right? So what that's going to happen in this case is, instead of those electrons being shared equally between the hydrogen and the fluorine, because fluorine is going to really pull those electrons a little bit more to its side, we end up getting sort of an unequal sharing of electrons here, by my bad Julie John fan here. And we get a lot more electrons sort of hanging out over there on the fluorine side. So we get this unequal sharing of electrons. And unequal sharing of electrons is what is referred to as a, if I write it right, there we go, a polar covalent bond. Or again, most people just call it a polar bond. And the unequal sharing of electrons here between the hydrogen and the fluorine, does create a different type of result in terms of that bond, because more of the electrons are hanging out towards the fluorine side. Would the fluorine side be more positive or more negative? So if all the negatively charged electrons are heading towards the fluorine side, it should end up becoming more negative. So we get this sort of charge separation that occurs where the fluorine side here now becomes partially negative. That's a delta negative. And the hydrogen side now becomes partially positive because the electrons are moving towards the right. We also could represent this very commonly with polar bonds by drawing what is sometimes referred to as a bond dipole arrow, where it points to the more negative side, and the back part that makes like a plus sign is the more positive side of the bond. And this creates a polar bond where we do have separation of charge. There is a side to that bond that's more positive. There's a side that is more negative. And that's really important for a lot of sort of functions that sometimes bonds can do. Also things like making things soluble or non-soluble, depending on what's happening there. Any questions on that there? So this creates our, again, polar covalent bond, is unequal sharing of electrons, resulting in a partially positive charge on one side, partially negative charge on the other. So this is a partial positive charge, partial negative charge, and this little guy is a delta sort of symbol. Now, why are they only partially positive and partially negative in this case, as opposed to fully positive and fully negative? Any ideas why that would be? The reason why they are partially positive and partially negative is because they're still being shared. So this is a covalent bond. There's still sharing of those electrons that are occurring. They have not completely transferred like we would see in an ionic bond. In an ionic bond, when we take something like sodium and chlorine together, we get that complete transfer of electrons, which creates a total positive charge and a total negative charge within the ionic compound. But here, those electrons, even though they're not being shared equally and are creating these partially positive, partially negative charges, they're still hanging on. So those electrons are still being shared, and that's why they're only partially positive, partially negatively charged. Any questions on that there? All right, so there's that kind of smear and what we just talked about. Again, the pink here would be like the electron density, much higher density of negatively charged over here, making it partially negative, a little bit partially positive on that side. So in thinking about the three different types of bonding that we've talked about here so far, there's sort of two extremes and kind of something in the middle. On sort of one end of the extreme, we have the ionic bond, if you will, where we have a metal and a non-metal, where we have the transfer of electrons, creating our cation, which is positive, and our anion, which is negative. Not positive, but negative would be good. And again, no sharing of electrons here. And an example would be, like I just wrote there, sodium chloride. On the other end of this stream, we have a nonpolar covalent bond, where we have equal sharing of electrons. And that is between two nonmetals. An example of that would be something like the F2 or the H2 that we saw there. By the way, if you do have like perfectly equal sharing of electrons, we're going to talk about how you kind of determine that in just a second. But if you do have perfectly equal sharing of electrons, that is also sometimes referred to as a pure covalent bond. So if somebody says, hey, this is a pure covalent bond, that's basically a nonpolar bond, and that's like perfect equal sharing of electrons between the two, like these two examples here would be. Since they are both the same element on each side, you would expect perfect equal sharing of electrons between them, and they would be also sometimes referred to as a pure covalent bond, which is again the same thing as a nonpolar bond, but sometimes people do that. And sort of in the middle of these two extremes, on one extreme we got the electrons being transferred, on the other extreme we have them being perfectly equally shared. We have our polar covalent bond, our dipolar bond. That also is between two nonmetals. That also is sharing of electrons, but unequal sharing. And an example would be our guy right here, RHF would be an example of that. So one end, we got the complete transfer of electrons, always happens with metal, nonmetals come together. Other end, we got perfect equal sharing of electrons, which always happens when you put two of the same elements together. By the way, you could also get a nonpolar bond with two different elements. There are certain ones that when they come together, they will share it equally. But in the middle is we don't have perfect equal sharing of electrons, but we don't have such unequal sharing of electrons that they get transferred. So kind of in the middle is like we're going to share the electrons, but definitely not equally. It's going to go one way or the other and create that separation of charge. Any questions on any of the different types of bonds there that we talked about here? So as I mentioned before, what really helps us determine, are we going to get those electrons to be shared equally or unequally, is electronegativity. And electronegativity of an element is related to electron affinity, that energy change when it gains an electron, and ionization energy, which is the energy required to remove an electron. So things that have high electron affinity and high ionization energy, which typically can be found on the top right of the periodic table, are things like fluorine, which typically will have high electronegativity values. Things like sodium and those guys to the left and down on the periodic table, which have the opposite trend there, low electron affinity and low ionization energy, will typically have low electronegativity. So a guy by the name of Pauling, come back here. A guy by the name of Pauling came up with a method to sort of calculate electronegativity for each of the elements. And he was able to basically assign electronegativity values of 0 to 4. 4 is the most electronegative, and 0 not so much. We already talked about yesterday the trend on the periodic table, and a reminder in terms of electronegativity, it does increase as we go this way on the periodic table. It decreases as we go this way. And once again, fluorine is our most electronegative element you can have. So you can use Pauling's table of electronegativity values to help you decide whether or not something is going to be a sort of polar bond, a nonpolar bond. You can even use it for ionic bonds, but you don't really need the numbers because, frankly, as soon as you see metal, nonmetals, ionic, you don't even actually need the numbers. But typically speaking, if you take what is sometimes referred to as the difference in electronegativity values, so that's the difference in electronegativity, and you basically just subtract the two values, and if you get a difference between like 0 to 0.4, is considered a nonpolar covalent bond, which basically means it's considered to be sharing the electrons equally. As I mentioned a second ago, if you have perfect equal sharing of electrons, that is what's referred to as a pure covalent bond. That would be when you get a value of 0. So when you subtract the two values, you get a value of 0. But you can also see that if you go up to 0.4, it is still considered equal sharing of electrons, but in reality, it's not perfectly equal sharing of electrons. There's a little bit of unequal sharing happening, but it is still considered nonpolar overall. If you go above 0.4 to below 2, that is considered a polar bond. So if you take the two electronegativity values, basically you subtract them, and you get a value that falls between above 0.4, which I guess is 0.5, to below 2, that is considered a polar covalent bond. That is considered between those two elements, you will have unequal sharing of electrons. That also would mean there would be a side that's more positive and a side that's more negative, partially positive, partially negative sides to that bond. Yes. Next question. Yes. Yep. Above 2 typically is an ionic bond. That above 2 value is not perfect. There are some ionic bonds that actually have a difference in electronegativity value a little bit below 2. But in general, if you have something above 2, it is sort of considered ionic. Personally, I don't even think you need the numbers to do ionic bond. Once again, as we talked about many times here, as soon as you see the metal, non-metal combo, I wouldn't even bother with the numbers. Just write ionic and move on with your day. It definitely should be ionic. So let's take a look at this table. So here's a table of electronegativity values. And again, you can see pretty much as you go up and to the right there, we have the highest number with fluorine coming in at 4 as being the highest number. So if we looked at sort of our 3 types of bonding that we had there, we had our ionic, which was sodium and chlorine. So if we went to our table here, our sodium is 0.9. Our chlorine, which is on the other side there, is 3. And by the way, when you do the difference in electronegativity, just take the larger number minus the smaller, so you get a positive number is all you have to do. So we take 3 minus 0.9. That is going to give us a 2.1 difference. That is above 2, which is our cutoff there for an ionic bond. Once again, you really don't need the table for this. As soon as you saw sodium chloride, it should be ionic. If we looked at our nonpolar bond, so we talked about there, we had fluorine, which is F2. So the fluorine is 4 on this side, fluorine is 4 on this side. Difference in electronegativity would obviously be 4 minus 4, which would be 0. And that would be a nonpolar bond, as we would expect it to be there. And that also would be, again, a pure covalent bond. If we look at our polar guy, which was HF, we would look at hydrogen, which is 2.1. We would look at fluorine, which is 4. And if we did our difference in electronegativity, 4 minus 2.1 is a 1.9, I believe. 1.9 is pretty much the upper limit there of polar bond. That tells us also that these electrons are pretty much being shared pretty much not equally at all. That fluorine almost has grabbed them all on, but is still hanging on the hydrogen there. They haven't fully transferred. So there are some degrees of sort of polarity, if you will, within a bond. This would be pretty unequal sharing of electrons. Clearly, if you hit something in like the 0.7 range, it's unequal sharing of electrons, but not extremely unequal sharing of electrons. So there is some degree that you have there. Any questions on how you would do that there? I'm going to give you some, and why don't you take a second to decide whether or not they're going to be an ionic bond, a polar bond, or a nonpolar bond here. Why don't we do carbon and hydrogen bond? Why don't we do let's do cesium and oxygen. Let us do oxygen and sulfur. Let's do carbon and oxygen. And let us do nitrogen and chlorine. All right, so for each of those, figure out based on electronegativity values, are they going to be ionic, polar, or nonpolar? Let's see, so a reminder of our cutoffs. So once again, if we have a difference in electronegativity of 0 to 0.4, that is going to be nonpolar. We got above that 0.4 to below 2, that is going to be polar. And once again, above 2 will be ionic. All right, so we'll start with the carbon and hydrogen. So carbon is 2.1. Hydrogen, that is hydrogen, actually 2.1, and carbon would be 2.5. Turn that down to a 5. So basically, if we take the difference here in electronegativity and just kind of subtract those two, we are going to end up with a 0.4, and that is going to make this guy a nonpolar bond. That is really why the cutoff there is actually 0.4. Carbon, hydrogen is the basis of organic compounds, and they're nonpolar. So that is basically the cutoff here. This also is considered nonpolar, but there really is not perfect equal sharing of electrons happening here, right? Electrons are actually moving a little bit towards the carbon side, right? It's a little bit more electronegative, but it's still considered nonpolar in this particular case. We look at cesium, which is 0.7. Oxygen there is 3.5. And we take the difference in electronegativity of 3.5 minus 0.7. That is going to give us like a 2.8, I think, maybe-ish, in terms of the difference there. Grab my calculator and make sure, but I think so. There we go, 2.8. That is definitely above 2, and that should make this guy obviously ionic because of that, right? By the way, again, this is one of those ones where you really don't need the numbers. We see it as a metal and a non-metal together, so it definitely should be ionic in this case. If we look at oxygen and sulfur here, oxygen being 3.5, sulfur there being 2.5. Difference in electronegativity is 3.5 minus 2.5. That is going to be 1. That definitely is above 0.4 and below 2. So we would expect this to be a polar bond in this particular case. Any questions on any of those there? Looking at carbon and oxygen, carbon being 2.5 and oxygen being 3.5 in this case. So actually we get the same spread there. That's going to be a difference in electronegativity of 3.5 minus 2.5, giving us 1, which should be a polar bond. And in this case here, we have nitrogen and oxygen. Nitrogen being 3. Oxygen being 3.5. Difference here, it's not oxygen, it's chlorine. Chlorine being 3 as well. There we go. Difference in electronegativity is 3 minus 3 equals 0 in this case. So the nitrogen and the chlorine actually have the same electronegativity value, and this would be a nonpolar bond. So this is a good example that you can have two different elements that will share those electrons equally and will result in a nonpolar bond. Question on that there. The reason for that is their placement on the periodic table here. This is nitrogen, and this is chlorine. They are what we sometimes refer to as being diagonal of each other. The nitrogen is further up, but the chlorine is further to the right. So their differences there kind of cancel each other out on the diagonal, and they end up with the same electronegativity value. We also see that there if you look at carbon and sulfur, they are diagonal of each other as well. They have the same electronegativity value. So there's several places where you can have a couple of nonmetals that are sort of placed diagonal of each other on the periodic table, not right below each other, but kind of down and over one, diagonal to each other is typically the relationship that you see, and you can have a nonpolar bond. So nonpolar bond definitely occurs when you have two of the same elements, but you can definitely have a nonpolar bond from two different elements, you know, based on their location. Any questions on that there? Blank screen. Now, there are certain things here, for example, that you also do not really need the numbers for in certain situations. For example, the one that we did here, which was carbon and oxygen, they are on the same period, right? And because they are on the same period on the periodic table, frankly, oxygen is further to the right, which means it should be more electronegative, just using the general trend of electronegativity. So even without the numbers, you can make a pretty educated guess that that should be a polar bond in that case. So if you're comparing something and you want to do it kind of quickly and they're definitely in the same period, the guy further to the right should be more electronegative, and if they were both nonmetals, it should result usually in a polar bond happening without even needing really the numbers to do so. You could also do a similar thing if you have two that are in the same group, like we did here with oxygen and sulfur. Oxygen and sulfur are in the same group there. Oxygen is further up on the group, which means electronegativity increases as you go up. So again, because they're in the same group, you don't really need the numbers. You can make a pretty educated guess that they are going to make a polar bond. And you can make an even better educated guess that it should be the oxygen that's more electronegative, and electrons should be going towards the oxygen. So a lot of times you can make a fairly pretty good educated guess if you're comparing something again in the same period or the same group. You don't really even need the numbers. You can just use the general trend of electronegativity to determine whether or not it's going to be polar. And it most likely will end up in a polar bond if they are in the same period or same group. And that's a really good way to kind of quickly do it. Obviously, if you need it, these numbers would be provided to you. You just need to know how to obviously use them. Just so we're clear here, what we're looking at in terms of electronegativity here is typically used for what's referred to sometimes as bond polarity. Bond polarity is simply talking about between these two elements, are those electrons going to be shared equally or unequally? It is not to be confused with, as we'll talk about a little bit in this chapter, and then again in the next chapter, molecular polarity. Molecular polarity is taking the entire sort of compound together and determining based on all the bonds that are present, is the bond, is the molecule polar or nonpolar overall, or are they sharing electrons equally or unequally? So typically we use electronegativity for bond polarity. There is only one place where it also will be molecular polarity, but it is typically just to determine between these two things, you know, is it going to share them equally or unequally? Any questions about electronegativity values, how to use them to determine polarity? Okay. So as we saw there, atoms with widely different electronegativities, which is typically what you get when you take a metal and non-metal together, will most likely result in an ionic bond, a losing and gaining of electrons. Atoms with similar electronegativities will definitely form some type of covalent bond, either sharing electrons equally or unequally. And again, if it is a polar bond like we had with carbon and oxygen, you can use the dipole arrows to represent. In this case, we would draw the arrow towards the oxygen as it is more electronegative. Also between, say, sulfur and oxygen, we would draw it, the arrow that way. Again, the oxygen in both cases being more negative, and these guys being more positively charged in each of those cases. All right. So as we talked about, that's basically what the typically going to form between ionic bonds and covalent bonds, non-metals sharing of electrons, because they do share those equal sort of periodic trends. As I mentioned also on there, you know, you can find some combinations of metals and non-metals that will get you something below 2, but it's a general rule for above 2 for ionic compounds. Sometimes when people talk about sort of how electrons are being shared in terms of percent ionic character, if something has 100% ionic character, it's pretty much an ionic bond, and there's no sharing of electrons that occur. If something has 0% ionic character, then it is pretty much a nonpolar covalent bond, perfect sharing of electrons. So sometimes people talk about percent ionic character in relationship to polar and nonpolar, and that's sort of the relationship that we see here. 0 electronegativity, definitely going to be covalent, and would have obviously 0 ionic character and 100% ionic character if it is obviously a large difference. All right, so now that we talked about sort of drawing Lewis structures for ionic compounds, talked about the bonding and how the electrons are going to be shared in an ionic compound, we're going to talk about the steps to drawing Lewis structures for covalent compounds and covalent bonding. And if you follow these rules, you should end up with a pretty good picture when it's all said and done. If you don't follow these rules and you do what sometimes people like to do, which I call kind of like piecework, if you will, like they draw all the individual Lewis dot symbols of everybody, go, like he's got like 3 electrons and he needs to get like 5 more, and this guy's got 2, he needs some more, and try to figure out how it all comes together with covalent bonding. Usually what will happen in that case if you kind of do piecework is you'll end up with something that has either too many bonds, not enough bonds, too many electrons, and stuff like that. It is best to think about everybody coming together and the total number of electrons that are there and being able to sort of distribute them equally, and that's a good way to do it. So first off, let's talk about some of these steps here. The first thing you want to do is think about the skeletal structure of the compound. Basically, think about how the atoms would come together, who would be maybe the center atom, and everybody else attached to it. In a lot of cases, what you'll be drawing in this class is there's like one center atom and like everything else is attached to it. Sometimes there are multiple center atoms that can occur, but a lot of times, you know, there's kind of like one thing and everybody else is sort of piled on top of it. To help you decide what should really go into the center atom, typically the guy in the center is the least electronegative atom. So the least electronegative atom is usually the guy that's in the center of a Lewis structure. We never find hydrogen in the center, as we talked about earlier, because again, if hydrogen is in the center, it's got way too many bonds. And we never find fluorine typically in the center because, frankly, fluorine is the most electronegative atom, so it will not find itself sort of in the middle. Probably the most important thing when you do a Lewis structure is the next part, and that is to count up the total number of valence electrons there are. That is in the entire sort of compound, the total number of valence electrons. Now, if you happen to be drawing something that's an ion that has a charge, you do need to adjust your total count so you have the right number of electrons. If something is a negatively charged ion, it means it has gained electrons, so you need to add that to your total. So if something has a -2 charge to your total, you need to add 2 more electrons so you have the right amount. If something has a positive charge, it means it has lost electrons, so you need to subtract that from your total. So if you have something with a +2 charge, you would subtract off 2 electrons when you do that. That number is the most important because when you're done with your picture, you need to have exactly that number of electrons in your picture. You cannot have more, you cannot have less. It's got to hit that number on the nose there. The next thing that you want to do is you want to go from the center atom to each of the outside atoms, and you basically want to make one single bond. Personally, I use lines, so one line, which represents bonding electrons from the center atom to each of the outside atoms. Once you do that, you will have used up some of your total electrons, and you want to figure out how many electrons you have left. All the leftover electrons that you would have at that point will go on the outside atoms first, in pairs of electrons until each outside atom has 8 electrons, except if it's hydrogen, then it should only have 2. But everybody on the outside has 8 electrons. As you go around to everybody on the outside and you've used up all the electrons or filled up all the electrons on the outside, and if you still have electrons that you need to put on your picture, then you go to the center atom and you put it on as dots as well. Lastly, what you want to do is figure out, did everybody meet the octet rule except for hydrogen? And if at that point somebody did not meet the octet rule, that is when we're going to try to make a double bond to fix it. And if the double bond doesn't fix it, you sort of exhaust all your chances to make double bonds, then you should make a triple bond to try to fix it. And at that point, it should fix it. Again, here's what I was talking about earlier. You don't want to kind of double bond or triple bond right out of the box. You kind of want to save it to fix problems that might be bad. Any questions on that there? All right, so let's go through one here together to go through the steps. Let's say we're going to do nitrogen trifluoride here. So the first thing really I would do is figure out the total number of valence electrons. So remember that the group number equals the valence electrons. So nitrogen is group number 5, so that's 5 valence electrons. There are 3 fluorines. Each fluorine is group number 7, so it has 7 valence electrons. So log them out there and go with 26 and hope for the best. So that is 26 valence electrons. In this particular case, we want to think about the logical arrangement of this. And by the way, logical arrangement is sometimes common sense as well. I have one element and 3 of the same elements. Usually the one guy is in the middle. Between nitrogen and fluorine, we know nitrogen is the least electronegative of those two, so it should find itself in the center. We should then have the fluorines around it. Doesn't matter if I put the fluorine on the bottom or the top. The answer is no. You could throw it up on top there if you want, rather than the bottom. So I got my logical arrangement. I have my total number of electrons. The next thing I'm going to do is take from the center atom to each of the outside atoms, basically make one single bond. So one line to each. Since each line represents 2 electrons, I have now used 2, 4, and 6 electrons. That means I have 20 more electrons I need to put onto this atom. If I subtract that from my total here, got 20 more to go at this point. And those are going to go on the outside ones in pairs. So we're going to go with 2, 4, 6. That fills up that fluorine. 8, 10, 12. That fills up that fluorine. 14, 16, 18, that fills up that fluorine. At this point, I have now placed 24 electrons. I still have 2 more to go at this point. I'm down to 2. I have nowhere to put it on the outside. Now I go to the center and I put it in as a pair of electrons. And now I have a picture that has 26 electrons. And that's exactly what I need. I want to make sure that everybody has met the octet rule. And if we just kind of roll around here, that is 2, 4, 6, 8 for that fluorine. Each of the fluorines are identical, 2, 4, 6, 8, 2, 4, 6, 8. And now if I look at the nitrogen and I count up the electrons that we got going there, that is 2, 4, 6, and 8. So the nitrogen also has 8 electrons. So this would be the correct Lewis structure before I started highlighting it with all the highlights there. Everybody has 8 electrons, met the octet rule. We have distributed the 26 electrons in this picture. Any questions on that there? All right, then why don't you try one here, or why don't you try CO32 minus? So take a couple minutes to see what you come up with. Take a look since we're getting to the end here on this one. So carbon has 4 valence electrons. There's 3 oxygens, each for group 6. Now at this point, this guy does have a -2 charge, which means it has gained 2 electrons. So we want to add 2 electrons to it. So that is 18, 20, and 24 valence electrons when we draw this one. In this case, we have carbon, which is further to the left than oxygen, so it should occupy the center spot with oxygen going around. At this point, we'll do our single bond to each of the outside ones. That's going to use up 6 electrons. That is going to give us now 18 electrons to go, which will go as pairs on the outside. So 2, 4, 6, 8, 10, 12, 14, 16, 18. At this particular point, we have now used up all 24 electrons. Is everybody good here? One that is not good is carbon, right? All the oxygens have 8, carbon only has 6. So we need to fix that. Can we do this by just putting dots? We cannot do that because now we have 26 electrons, which is too many. And that is still red. Let's try that again here. So what we need to do in this case is basically try to fix it by making a double bond. So we can make a double bond really on any of the oxygens. Can I just lay up the double bond in this case? The answer is no, for the same reason. We're at 26 and the oxygen now up on top has too many electrons. So when we make a double bond, and even when we make a triple bond, what we're actually going to be doing is taking a pair of electrons, for example, like these, and we're going to be bringing them in to make that double bond. And the result of that will give us now a double bond that's up on top. Everybody else will still be the same single bonded there on the left and right-hand side. And now when we look at the carbon now has 8 electrons, the oxygen on the right there has 8 electrons. The double bonded oxygen, the 2 double bond there, or the double bond plus the 2 pairs of electrons is 8. Now we have 8 electrons for everybody. We only still have 24 electrons in this case. And since it is something with a charge, we typically put a little bracket around it and a -2 to make it look all pretty. And we have met the octet rule here. The question that was earlier asked about resonance structures is, in this particular case, we actually really could have made the double bond over here. We could have done the double bond over here because we have basically the same oxygen on any side, which means we can draw an equivalent type of structure where perhaps you double bonded there to the left. Or you maybe double bonded to the right. And all three of these structures are what are referred to as resonance structures, and sometimes they use this little arrow to go between them. These are resonance structures. And basically what a resonance structure is a situation like this where you do have multiple places where perhaps you could double bond and make a, or maybe even triple bond in rare cases, but mostly double bond. And the reason for that is the double bond electrons are sometimes referred to as being delocalized, which means at any given point in time, maybe we're drawing the double bond electrons from the top. So we get like that double bond up there at the top, but it could then move over to either side, maybe to the left or maybe to the right. So the real structure is probably somewhere between all three of these things because those electrons are moving around. And this sometimes happens where you do double bonds and stuff like that. You could draw multiple sort of structures. If you're asked to draw the resonance structure, you should lay up all three structures. If you're asked to draw the Lewis structure, you could lay up any of the three structures and it should be fine in terms of that. Any questions on that there? All right, we will lay it up there for now.